Okay, let us start. Remember, we have finished with the root locus. And in root locus, what we do is that we are given the open loop transfer function. And when we are given the open loop transfer function, by using root locus, we are obtaining the closed loop pole trajectories. Okay? So we always, in control, we are always trying to obtain closed loop characteristics by first getting the open loop transfer functions. So today we are going to start with another stability criterion, which is going to be more or less in frequency domain. Root locus is something in Laplace domain usually, and this new criterion that we are going to see is going to be mainly in frequency domain, and it's going to form a basis for other topics like frequency domain controller design, etc. We're going to be doing a similar thing. We are going to be starting with the open loop characteristics, for example, open loop frequency response, and then we are going to try to say something about the closed loop stability. When a single parameter changes from -infinity to infinity in this case. In root locus, we had a k parameter which changed between 0 and infinity. And in Nyquist stability criterion, we won't have actually any constraint on k. So this k is going to change. It's still going to be real, but it's going to change between -infinity and +infinity. So today's topic is Nyquist stability criterion. Again, we are going to be doing the same thing. We are going to get something related to the open loop. This is going to be either the transfer function of the open loop, or it's going to be the frequency response of the open loop transfer function. And then we're going to try to say something about the closed loop stability. Okay, that we are always doing the same thing in this course. When we go into the body plots, we are going to get the body plot for the open loop system. And we're going to design our controller for obtaining some performance requirements, satisfying some performance requirements by the closed loop system. And when we go into the state space concept, we're going to do the same thing. We are going to get the open loop state space representation, and then we're going to try to design the closed loop state space representation by choosing some parameters. In this course, we are always doing the same thing. We have the open loop characteristics. We would like to say something after we close the loop. What happens when we close the loop? In the Nyquist stability criterion, we are going to be mainly interested in, again, transfer functions or frequency responses, and we will be able to say something about the closed loop characteristics of the system. I'm going to start with a definition. So we're going to draw again some plots. These plots would be stranger than the root locuses, and interpreting them is going to be more difficult than interpreting a root locus plot. Okay. So here let us write a definition. These plots are again going to be in complex planes. So let me say definition. We are considering a contour is a closed path with a direction in a complex plane. Okay? So let me show you. We will be talking about contours in S-plane, for example. So this is real of S, imaginary of S. And contour is a very simple thing. It's a closed path like this with a direction, clockwise or counterclockwise direction. Okay, so we will be defining these contours. When I define a contour in the S-plane, I can call it as gamma S. This is capital gamma, and I define the plane that it's living in by the subscript S. Again, I can define the direction. In this case, we have the counterclockwise direction, but we might have, of course, clockwise direction contours as well. So here, I will immediately make a remark here. The Nyquist stability criterion is related to the transformation of these type of contours by some rational transfer functions. We are going to start with the open loop transfer function, and we are going to start with an initial contour. And then we are going to transform that contour by that rational transfer function. And when we transform such a contour by the open loop transfer function, we are going to call that plot, the plot that is going to appear as the Nyquist plot. Okay? And then based on the Nyquist plot, we can decide on the stability characteristics of the closed loop system. So here in this remark, I'm going to write the following. A continuous function. In general, this is going to be a rational function that we will be talking about, and it's going to be the open loop transfer function. So a continuous function f of s maps a contour gamma s in S-plane to another contour gamma f of s in f of s plane. Okay. In general, as I told you, we are going to choose this f of s to be the open loop transfer function of the system. Okay? And what this remark means the following. When I have a contour in S-plane, this is real of S, imaginary of S, and I have a contour. So let me say that this contour has a clockwise direction here. Then I will take each point on this contour and I will transform it from a transformation f of s. Okay? This is going to be a continuous function in general, and it's going to be the rational transfer function of the open loop system. And I will transform each and every point on this contour into the f of s plane. Okay? So in between I have the transformation f of s here. So this is real f of s, this is f of s plane, imaginary f of s. And I will transform each point on that contour into another point on an f of s contour. Okay? And that is going to mean that because this is a closed path, the resulting contour is going to be a closed path again. Okay? So I'm going to get some other contour here on this f of s plane. Okay? And based on this conversion from here to here, we will be able to say something about the closed loop transfer function, or the closed loop poles. So the first thing that I'm going to do is that we're going to use something called Cauchy principle of argument in obtaining Nyquist stability criterion. Okay? So this is a deep result in complex analysis, or complex calculus, if you would like to call it like that. We're going to use something called Cauchy principle of argument, and the first thing that I'm going to do here is to illustrate you what Cauchy principle of argument is. Okay? It is related to the transformation of contours by some continuous functions, which are rational transfer functions, into new contours. Okay? So let me try to illustrate it on some examples. We will not be able to, in this, because as electrical engineers, in this department there was a complex analysis course in the past, even before my time. For example, I think the last ones who took it were the graduates of 1996 probably. I couldn't take it, but in this department there was a complex analysis course. And all of these results were proven there, but unfortunately that course was not in the curriculum, is not in the curriculum for some time. So unfortunately we are not going to see the proof of this thing, but I will try to illustrate what it means on some examples as good as possible, or as good as I can do actually. Okay? But if you would like to learn the mathematical background of that thing, you have to take a whole course related to complex analysis. So here, let me try to give you a contour example. The contour that I'm going to use is going to be a very simple one, and it's going to be the unit circle. Okay, unit circle in the complex plane, and I'm going to be taking the clockwise encirclement of it. Okay, so in this case, this point is 1, -1, j. And minus j. And as the first transformation that I'm going to consider, I'm going to take a very simple one. The simple transformation that I will consider is going to be s minus 1/2. Okay? A very simple transformation, f of s. Okay? So here, on this side, I will write some numbers. These are going to be some integers. And these integers are going to be called n, z, and p. Okay? And Cauchy principle of argument is going to be a relationship between these three integers. Okay? So here, n is going to be the number of, so this is my gamma s in this case. Gamma sub s is my unit circle, clockwise unit circle. Okay? And I will define what it is, and I will define what z is, and I will define what p is. I will define the z as the following. This is the number of zeros of f of s encircled by gamma s. Okay? Z is going to be the number of zeros of f of s encircled by gamma s. And p is going to be the number of poles of f of s encircled by gamma s. Okay? And then I will define what n is. N is going to be related to gamma sub f of s. It is going to be related to the new contour. Okay? So here let us transform this unit circle by this transformation. Okay? So currently I can write what z and p are. So this is my f of s, and I can actually see that it has a 0 at the point 1/2, and it doesn't have any poles. Okay? So here, what is z for this example? What is z? It is the number of zeros of f of s encircled by gamma s. What is z? It is just 1. What is p? 0. So I don't know, I haven't currently defined what n is for this example. But we are going to define it once we transform this curve, this closed contour, into the gamma f of s plane. So here, let me draw an f of s plane. So this is real f of s, and this axis is imaginary f of s. And here is what I'm going to do. I'm going to consider myself taking each point on this contour, and I'm going to transform it by this transformation. Okay? And then I will place that point into my f of s plane. Okay? So this point is s is equal to 1. When s is equal to 1 is transformed, so let me put some labels here. This is the point A. Let me say point B, point C, and point D here. Okay? If I transform the point A, which is s is equal to 1, by this transformation, what do I get? If I substitute s equal to 1 into this transformation, I get 1 minus 1/2, which is the point 1/2 in the f of s plane. Okay? This is the transformed point A. I can transform any point here on this contour by this transformation. For example, if I transform this point, which is the point B, the new point is going to be minus j minus 1/2. Okay? So it's going to be somewhere here. Its imaginary part is going to be minus j, and its real part is going to be minus 1/2. Okay? So this is going to be my new point B here. And if I transform this, I'm going to end up at minus 3/2. And if I transform this, I'm going to end up plus j minus 1/2. Okay? So this is, let us say that this is the point D. And you see that this transformation, what it is doing is that it is shifting all of this curve to the left by 1/2. Okay? So as a result, I can actually draw here the new curve as follows. Okay? It's going to be something like this. The center of this circle, because of my impressive drawing skills, the center is not looking like it is at minus 1/2, but it is at minus 1/2. Okay? So here the curve is going to be looking like this. Okay? So here now this is the curve gamma f of s. Okay? It is the transformed curve. All right? And now I'm actually ready to actually define what this n is. This is the number of clockwise encirclements of the origin by gamma f of s. Okay? This is the number of clockwise encirclements of the origin. It is clockwise because my initial curve has clockwise direction. If my initial curve had the counterclockwise direction, then I would define it as the counterclockwise encirclements of the origin. So here, the origin in the new plane is here. And I see indeed that the origin is encircled in clockwise direction by gamma f of s how many times? Once. So I see that in this case, n is equal to 1. Okay? As I told you, Cauchy principle of argument is going to be a relationship between n, z, and p. Okay? Now, currently, we can roughly see some form of relationship, but we're going to be able to identify what that relationship is when I try to look at more examples. Let us say that the second example is going to be as follows. I will take exactly the same curve. In all examples, I will use the same curve. It is going to be the unit circle. Gamma S is always going to be the clockwise unit circle. Okay? Gamma S is clockwise unit circle in the S plane. Okay? And now I'm just going to change my f of s in this case. It is f of s is, I will take it as s plus 2. Okay? This is my unit circle. It is clockwise. And I see that s plus 2 has a 0 at the point minus 2. Okay? So in this case, what is, as z and p are related to gamma s, okay? And what is z and p for this example? Z is the number of zeros of f of s encircled by gamma s. Okay? What is z for that example? It is 0 in this case, because the 0 is now outside. It's not encircled by the curve. Okay? What is p? The transformation doesn't have any poles. Okay? So it's going to be 0, and I will try to find n. So now you know how to transform this curve by such a transformation. So here, if I transform each point on this unit circle, then I see that my new circle is going to be somewhere here. This point, so that is the point A, B, C, D. To all points, I'm going to add 2. Meaning that the point A is going to come to the point 3 in f of s plane. Okay? And I have imaginary f of s here. The point minus 1 is going to come to the point 1. The point B is going to be somewhere here, and the point D will be here. And my new unit circle is going to be somewhere here. Again, it doesn't look like a circle, but it is a circle. Okay? So now I can answer the question of what is n. N is the number of clockwise encirclements of the origin by the transformed curve gamma f of s. Okay? How many times is the origin encircled by that curve? It is 0. So in this case, this is 0. Yes.
Is there any f that is capable of changing the orientation of the contour?
Yes, there is, and it's going to be one of the examples. That is going to happen. So here I will have a third example and the fourth one. So the example is as follows. Example. In this case, again the same curve, same gamma s, but in this case I have f of s is equal to 1 over s minus 1 over 2. In this case I take the reciprocal of s minus 1 over 2, and I will look at what this does to this unit circle. So in this case I can again draw my unit circle, and I see that this transformation has a pole in this case at s equals to 1 over 2. Okay? And it doesn't have any zeros, any finite zeros, if I want to specify that. So here, then I can decide on what are z and p. What is z for this example? It is 0. There are 0 zeros of that thing. What is p? It is 1. So now I'm going to transform this curve by this thing, and this is going to be significantly, of course, more difficult. But my earlier examples is going to provide me a basis for that. And here is what I'm going to do. I already know the transformation of unit circle by s minus 1 over 2. Okay? And this is the s minus 1 over 2 transformation of the unit circle. If I consider each point here, and if I take its reciprocal, then I'm going to obtain the transformation of this curve by 1 over s minus 2. Okay? So if this is the transformation s minus 1 over 2. And if I take each point on this curve, and if I take its reciprocal, if I take 1 over that point, and if I place it in my new axis, I'm going to obtain the transformation roughly. Okay, it's not going to be an exact transformation shape, but I will be able to say something. So here my f of s plane, real f of s, imaginary f of s here. So I will go and try to take each point here, and I will take its reciprocal. So this is the point 1 over 2. 1 over 1 over 2 is 2. So the new point is going to be somewhere here. Okay, and this is the point 2. And then I'm going to come here. I'm going to look at this point. Can we find the coordinates of this point? Its real part is 0. What about its imaginary part? So here the radius of this circle is actually 1. Okay? And the real part here, the distance here is 1 over 2. Okay? Then what can you say about this point? Very good. So it is negative. This point is going to be minus square root 3 over 2j. Okay? Then what I'm going to do is that, so let me say that this is the point B prime. Okay? So here what I'm going to do is that I'm going to take the reciprocal of this point. Okay? It is going to be 1 over square root 3 over 2j, and I have a minus sign. So I have 1 over j, which is minus j. So I have 2 over square root 3j here. Okay? So here my B prime point is transformed into such a point. Okay? So this is 2 over square root 3j here. I have the point minus 3 over 2. Where is this point transformed into? Minus 2 over 3. It is transformed somewhere here. Minus 2 over 3. And if I look at this point, its reciprocal is going to be somewhere here. If you try the points in between, you're going to see that this curve is, as this curve goes from A to B prime, and then B, this curve is going to be making such a motion. Okay? And its direction in this case becomes actually counterclockwise. Okay? So I have defined n as the number of clockwise encirclements of the origin. Now the origin is encircled once, but in counterclockwise direction. Then what should I count as my number of encirclements? It's going to be minus 1 in this case. Okay? So here, this thing is going to be minus 1. So here, let us try to solve our final example. And this final example is going to contain both a 0 and the pole of the transformation. But I think you start to see the relationship, what is going to happen to the general relationship there. So here, let me have the final example. And in this final example, the contour is the same. Gamma s is the same. But f of s is going to be the following. S over s minus 1 over 2. In this case, the transformation has both a 0 and the pole. Okay? So if I draw my gamma s, it's going to be looking like this. And if I mark this pole, it's going to be at 1 over 2. And if I mark the 0, it is going to be at 0. And now, what is z and what is p? For this example, z and p, what are they? They are both 1 for this example. And now I will obtain this transformation. By looking at this thing, it might really look difficult, but I'm going to do the following. Instead of this, I will write the following: s minus 1 over 2 plus 1 over 2, s minus 1 over 2. Okay? So when I write the transformation like this, I see that it's going to be 1, and I have plus 1 over 2 times 1 over s minus 1 over 2. Okay? So we see that this transformation, it first takes the 1 over s minus 1 over 2 transformation, it scales everything by 1 over 2, and it shifts everything to the right by 1. Okay? It's the scaling of this thing by 1 over 2, and then shifting it to the right. Okay? So now let us try to do it. Real of f of s, imaginary of f of s. So now I'm going to shrink this point by 1 over 2. It's going to come to 1. And then I'm going to shift it to the right by 1. It's going to remain where it is actually. This is A. So when I shrink this thing by 1 over 2, it becomes 1 over square root 3j. Okay? If I shift it to the right by 1, it's going to be somewhere here. I have 1 over square root 3j here, and the real part is going to be 1. Okay? And then if I take this point, it's going to be minus 2 over 3. If I shrink it by 1 over 2, it's going to be minus 1 over 3. If I add 1 to that, then I will get plus 1 over 3. It's going to be somewhere here. And then the other one, it will be somewhere here. And it's going to be looking like this. A shrinkage of this thing and shift to the right by 1. Okay? Nerede?
Ben göremiyorum tatlıyla eksi 2 bölü 3'ü 2'ye bölüp sonra 1 sağ kaydırmıyor mu?
Yes, 2 over 3. Thank you. Yes, you're right. Thank you. So that is 2 over 3, and then the overall curve will be looking like this. And how many times is the origin encircled by that curve in clockwise direction? 0. So now, tell me what the Cauchy principle of argument is. It's a relationship between n, z, and p. N is equal to... Yes? This is called the Cauchy principle of argument. Okay? So we are actually going to be able to write this, but it is a relationship between poles and zeros of a transformation encircled by a contour and the encirclement of the origin by the transformed contour. Interestingly, we will be able to use such a thing in order to be able to investigate stability in control systems. And the investigation of stability by using Cauchy principle of argument is going to be called actually Nyquist stability analysis. Okay? And these plots, these transformed curves that we are going to draw, they are going to be called the Nyquist plots. And by looking at how many times that Nyquist plot encircles some points, we will be able to decide on the stability of a closed loop system. But the first thing that I'm going to do is that I will write what Cauchy principle of argument is in a theorem. Yes. Yes, there is a problem there. So why is that? If the original contour passes through 0, let us say that I'm going to change your question a little bit. So I will say that this 0 is exactly on top of the contour. Okay? I will take my transformation as s minus 1. Okay? And one of the zeros is going to be on my original contour. Okay? In that case, what happens to the transformed contour? If you transform this unit circle by this transformation s minus 1, you know what you're going to get. You're going to get something like this. Okay? But this contour is going to pass through the origin in the new space. And when you have a curve like this, you won't be able to decide how many times the origin is encircled anymore. Okay? So here, because this contour is actually passing through the origin, you won't be able to decide how, because if this shifts by epsilon to the right, the result is 1. If this shifts by epsilon to the left, the result is equal to 0. What is going to be the result when the contour passes on top of the origin? Then I will not be able to decide on how many times the origin is encircled. That is why Cauchy principle of argument always assumes that there is neither a zero nor a pole of the transformation on this original contour. Okay? That is going to be one of the assumptions of Cauchy principle of argument. There shouldn't be any poles or any zeros of the transformation on the original contour. Okay? If it is the case, then the result might be invalid. So now yes.
This contour again unit circle?
Yes, the contour is again a unit circle and it has a zero of the transformation on top of it. In that case, because I won't be able to decide on the number of encirclements of the origin, the contour is going to be, the gamma f of s is going to pass through the origin. And in that case, I won't be able to decide on the number of encirclements of the origin. That is why Cauchy principle of argument always assumes that there is neither a zero nor a pole on the original contour gamma s. Okay? So let us write a theorem. This is called Cauchy's argument principle or Cauchy principle of argument. Given f of s, which is the ratio of two polynomials, we are talking about poles and zeros, then we have to talk about the rational functions. And a clockwise or counterclockwise contour, gamma s, in the S-plane, which does not cross any zeros or any poles of f of s. So that is the statement which gives some condition on the original contour. The contour should not cross any zeros or poles of f of s. The contour, the transformed contour, gamma f of s, and will encircle the origin n equals to z minus p times, where here in clockwise or counterclockwise direction. If the original contour is in clockwise direction, then I have to count the number of clockwise encirclements of the origin. If the original contour is in counterclockwise direction, then I have to count the counterclockwise encirclements of the origin. Okay? Direction. But in this course, we are going to be mainly using the clockwise encirclements. Direction where z and p are the number of zeros and poles of f of s encircled by gamma s. Okay. So now, how do we use this strange thing in stability analysis? So that is going to be the topic of the rest of the lecture today. So here we are going to use this Cauchy principle of argument in stability analysis of closed loop systems. So again, I'm going to start with a closed loop system given like this. That is G of S, and I will have H of S here. Okay? And this G of S, H of S, this is the open loop transfer function, as you might remember. This is going to be in the form K times N of S over D of S. It's going to be in this form again. Okay? So here is what I'm going to do. The first thing that I'm going to do is that I'm going to define my original contour here. And in my original contour, I would be interested in unstable poles or zeros. Okay? So in order to be able to take into account unstable poles, in this type of analysis, we always define our contour as follows. The contour passes from the imaginary axis and it encircles the whole right half plane. Okay? We take our original contour, gamma s, in this form. And the radius here is infinite. Okay? So, and the contour passes on top of the imaginary axis, and it actually encircles the whole of right half plane in an infinite semicircle like this. This is going to be the gamma s that we are going to consider in stability analysis of closed loop systems. So if any pole or zero of the transformation are encircled, they are going to be the unstable closed loop, open loop or closed loop poles or zeros. Okay? So this thing is called Nyquist path. It is not Nyquist plot. It is Nyquist path. The transformation of this thing is going to be the Nyquist plot. Okay? This is Nyquist path. Okay? And initially, we are going to choose our transformation as follows. Which equation determines the closed loop poles? We know that the equation determining the closed loop poles is this. G of S, H of S is equal to 0. This is the denominator of the closed loop transfer function. And if I equate this thing to 0, this equation determines the closed loop poles. And this is what I'm going to equate initially to f of s. This is going to be my initial transformation. Later we will modify it a little bit. But my f of s is going to be 1 plus g of s, h of s is k n of s over d of s. Okay? This is going to be my initial transformation. And I would like to make a stability analysis of the closed loop system when k changes between negative infinity and positive infinity. Okay? K is going to change on the real line, and I would like to determine by this procedure, whatever I'm going to do, I would like to determine the closed loop stability by transforming this contour by this f of s. Okay? And here, what is going to be important is the following. When I look at this transformation, it is d of s plus kn of s, okay, divided by d of s, okay? So here, I will again define what my f of n, z, and p are. I will define what n is after drawing the transform contour. That is going to be n, okay? I will define what z is, and I will define what p is. Remember that z is the number of zeros of f of s encircled by the original contour. Okay? Number of zeros of f of s encircled by the original contour. What can you say about the zeros of this rational function? What are the s values which make the numerator 0? What are they? Which s values, what do we call the s values which would make the numerator 0? What is this polynomial? We remember this from root locus. It is the characteristic polynomial of the closed loop system. Okay? what do we call the zeros of the or roots of the characteristic polynomial? They are the poles of the closed loop system. Okay? So here, Z is going to be the number of closed loop poles encircled by the Nyquist path. Okay? Z is the number of zeros of f of s encircled by gamma s, and here Z is going to represent the number of closed loop poles encircled by gamma s. Because gamma s covers the whole right half plane, this is actually going to be the number of unstable closed loop poles. Okay? And that is, we want that number to be equal to 0 for stability. Okay? So we will be interested in Z to be equal to 0. Okay? And then what about P? Poles of, P represents the number of poles of f of s encircled by this original curve. Okay? So here, poles of f of s are the s values which would make the denominator 0. Okay? What do we call the s values which would make the denominator 0? They are open loop poles. Okay? So P would be the number of open loop poles encircled by gamma s. Because gamma s encircles the whole right half plane, this is going to be the number of unstable open loop poles. Okay? So here, what we are going to do is the following. We now know what Z and P would represent. So we will start with such a contour, and after starting with such a contour, I'm going to draw a single plot here. Okay? This plot, let us say, it is going to be something like this. And n is the same. N is the number of clockwise. The original contour is going to be clockwise. Okay? So the contour is something like this. This is going to be again the same. Number of clockwise encirclements of the origin by gamma f of s. This is my gamma f of s. Okay? So here, we know that the relationship between n and z minus p would be like this. I will start with this contour, and I will transform that contour by this transformation. Okay? And I will obtain this new plot here. Okay? After obtaining this plot, I will look at the number of encirclements of the origin. This is going to be my n. And this is going to be known by us. Okay? This is going to be known. And in order to be able to find this transformation, I will know the open loop transfer function. I know what the open loop transfer function is, so I know the number of unstable open loop poles. Okay? So this number is also going to be known by us. Okay? The only thing that I won't know here is going to be the z. Okay? From this equation, if I know these two quantities, then I will be able to calculate z is equal to n plus p. Okay? I will know n after drawing that plot, and I will know p since I know the open loop transfer function. Then I will know how many unstable closed loop poles the system would have by summing these two numbers. For closed loop stability, what should be this sum? It should be 0, obviously. Okay? So if the sum is 0, then we are going to say that the closed loop system is stable. If the sum is larger than 0, then we will know that the closed loop system is actually unstable. So here, the only thing that I couldn't explain so far is the following thing. I would like to make a stability analysis when k changes between minus infinity and plus infinity. But if I change k, the transformation is going to change. So for each different k value, I need to draw a new plot, and then I need to calculate n for each of those new plots. And for each k value, I have to get a new z value. This is quite tedious, right? So here, for each new k value I would like to check stability for, I need to draw a new plot, and then I need to calculate n from that plot, and I need to calculate z from this. This is really a tedious procedure, and I really do not want to do this. I do not like the fact that the plot I obtain here is dependent on k. I do not want my plot to be dependent on k. Şimdi burada kritik bir yerdeyiz. Bir 5-10 dakika verirseniz teneffüsü bir 5-10 dakika itmemiz ileriye mümkün olur mu? So I would like to give this idea as well before the break. So here is the idea. N here is the number of clockwise encirclements of the origin by gamma f of s. Okay? It is the number of clockwise encirclements of the origin by gamma f of s. And f of s is 1 plus k n of s over d of s. Okay? F of s was that transformation. Okay? Now, if I want to remove this one, okay? Suppose that I modify my f, and I really do not take this one into account. Okay? In that case, what would be this new curve? This new curve is going to be this one shifted to the left by 1. Okay? In the original curve, I'm checking the number of encirclements of the original origin. Okay? In the new curve, where should I check for the encirclements of? Minus 1. Okay? Teneffüse çıkmak için şey mi yapıyorsunuz? Herkesin kafası acayip çalışmaya başlıyor. So here, this is the number of clockwise encirclements of the point minus 1. Instead of the origin, I need to check the encirclements of the point minus 1 by gamma k n of s over d of s. If I don't add this 1 here, I need to check the number of encirclements of the point minus 1, okay, by this curve instead. So now I want to get rid of even k here, okay? So what happens if I remove this k here? If I draw here only gamma n of s divided by d of s, okay? Then where should I check the number of encirclements of?
Minus 1 over k.
It is going to be minus 1 over k. Okay? So we see that, and we know that this curve will not depend on k anymore. Okay? I will just change the point that I look for the number of encirclements. When I change my k, the curve is going to remain the same. I will only look at the number of encirclements around which point that I'm taking care of. Okay? So here is the procedure. I will start with the Nyquist path, and I will transform this by f of s, which is n of s over d of s. Okay? It is going to be this contour. Okay? And this contour is going to be, let me say that it is going to be looking like something like this. Okay? And then this contour is going to be called the Nyquist plot. Nyquist plot is the plot we obtain by transforming this infinite semicircle by this n of s divided by d of s. This is the fixed plot which is independent of k, which we obtain by transforming this infinite semicircle by this rational transfer function. Okay? This plot is going to be called the Nyquist plot of the system. And then if I would like to check the stability, for example, for k is equal to 5, then what I do is that I look at the point minus 1 over 5, minus 1 over k, okay? And I look at the number of encirclements of that point by this curve. We see that it is 0 in this case, okay? Then I will substitute n is equal to 0 in that equation. Okay? I know what p is by counting the number of open loop poles which are unstable. Then I know what p is by determining for each k what the number of encirclements is. I will be able to find what n is. And I can look at, for example, k is equal to 100. In that case, let me say that the point minus 1 over 100 is somewhere here. Then n is going to be equal to 2, actually. N is going to be equal to 0 for this k value. And if I increase k here, k is going to be, for example, let us say 1000, then minus 1 over 1000 if it is here, then for that k, n is going to be 0 again. Okay? Or for negative k values, we will have the number of encirclements of such points. They are actually going to give me 0 encirclement as well. Okay? That is what we are going to do in Nyquist stability analysis. Okay? In the second lecture, we will try to draw our first Nyquist plot, and we will see these ideas in more detail. Let us now give a break. We can start again at 46 past 4. 46 geçe tekrar başlıyoruz.
Neredeyse bütün radyoları onun bir sebebi var mı?
Yani şey de yapabilirdim, sol tarafta da yapabilirdim. O zaman stable polların sayısını bulurdum. Yani traditional olarak unstable polların sayısıyla uğraşılmak seçilmiş. Biz de o yüzden. Ama sol tarafı alsaydık, bu sefer Z'yi 0 çıktığında değil, Z'yi tüm open loop, tüm closed loop polların sayısı çıktığında sistemi stable kabul etmem gerekirdi. Tamam, onu da yapabilirdik. Ama traditional olarak Nyquist böyle alınıyor ve unstable, Z'yi unstable polların sayısı.
Yani orada open loop transfer function'ı bilip nasıl closed loop şeyleri bilmiyoruz?
Closed loop polları K yüzünden bilemiyoruz. For each K, we have niye İngilizce konuşuyoruz? Her K için evet, gene tek parametre ve de K'ye göre stability analizi yapmak istiyoruz. Her K için closed loop polları falan hesaplamak istemiyorum. Direkt bana hangi K'ler için closed loop system stable söyle demek istiyorum.
Hocam bundan önceki yazdığımızda kısımda grafikler normalde clockwise dönüyorken f of s frame'ine geçince counterclockwise dönmeye başlıyor.
Dönebilir. Yani şeyi gördük ya, n eşittir z eksi p. Burada z0 p 1 iken tam tersine döneceğini söyleyebiliyorum. Yani pol sayısına göre aslında yani unit circle'la bakarken şunun içinde bir tane polu olduğunda tam tersine döndüğünü gördük aslında. Yani curve'ler bu arada şeyi soruyorsanız bu curve'leri ben kafadan attım. Yani tamam, bunların herhangi bir özelliği yok. Ben bunları şöyle de çizebilirdim. O zaman n eşittir eksi 2 almam gerekir.
Ya burada n'in Z ve P'den dolayı gelecek olan işareti belirliyor.
Evet, aynen öyle. İşaret belirliyor. İşaret negatifse original konturun tersine yönde dönmeye başlıyor. Tamam.
Çok teşekkür ederim.
Belki soru yapıyor tabii uygunsa eğer. Uygun. Dedik şu şeyde şematikte böyle bir simplification falan yapılabilecek bir şey var da ben mi?
Yok, hayır. Ya direkt denklemlerle algebraik hesaplamaya çalışın.
Tamam. Sonrası bildiğiniz.
Evet.
Bir de şu 4'ü yaptım ama E şıkkı mı K cevapları imajiner çıktı da.
Olmaması lazım. Evet. Yani yok. Yani en azından bir değerde şey olmaz. Imaginer result varsa imaginerleri atmanız gerekir.
Ya bildiğimiz şey yapmıştım işte. şu z-3 hani real part.
Doğru, öyle yapılacak. Doğru.
Öyle yapılır. Matematiksel işlem hatası o zaman.
Bir işlem hatası olsa gerek, evet. Yani k'nin en azından bir değerinin reel çıkması gerekiyor diye hatırlıyorum.
K ikinci dereceden
Çıkabilir ama ikinci dereceden çıkarsa en az birisinin reel çıkması için ikisinin de reel olması lazım. Demek ki bir yerde bir şey var.
burada ya farklı bir şey yok yani. Sadece
Yok,
matematiksel
hayır.
bir yanlış.
Aynen öyle.
Tamam.
Evet. Bir yerde bir işlem hatası.
Hocam, hani bizim kollarımızı koyuyoruz ya.
Aha.
Belli bir region'da eğer hani content yoksa, hani şeyden bahsediyorum. Blocks simply connected değilse, böyle bir durum var mı?
Aklıma şey getirdi sorunuz. Bazen şu oluyor. Pollar değil de pollara da düşünülebilir. Sistemin karakteristik polinomundaki katsayılar kimi zaman belli upper ve lower bound'lar arasında oluyorlar. Tamam mı? Bunlar belli upper ve lower bound'lar arasında oldukları zaman artık tek bir değerine bakmak bir mana ifade etmiyor. Bir range'de stability'ye bakmanızı gerektiriyor. Onun da Raoult Hurwitz'le çok kolay bir çözümü oluyor. Çok güzel bir şekilde bütün coefficient'lar için. Böyle bir şey yapılıyor. Ama şurada şu original curve'ün simply connected olmadığı durumu ben hiç görmedim açıkçası. Yani şunun böyle kendisini kestiği falan durum görmedim. Yani Nyquist stabilite analizde görmedim. Belki kompleks analizde öyle şeyler düşünüyorduk ama. Siz simply connected derken alan ayrım ama simply connected region olmazsa yani konturunuzun ayrık olması gerekir. Yani tek bir konturla yapamazsınız. Evet. Yani simply connected yani şu region'ın simply connected olması gerekiyor diye düşünüyorum ben. Evet.
başına şey takılıyor. Tabii tam bir cevap hani alamayacağım yani anladım da çok uzun şey olduğu için. Hani bu sonucun işte kompleks analizdeki işte bu kadar derin şeyleri yani yüzeysel olarak tam olarak neyleri kullanıyorsun? Yine mi çok
Yok, kontur integral diye bir şey var. İspatı kontur integrale dayalı bunun. Yani kontur integral aslında Cauchy'nin ilgilendiği, kompleks analizin ilgilendiği temel bir şey. Kontur integral meselesine dayanıyor ve de singularity meselesine dayanır. Yani direkt Cauchy Principle of Argument'ın internetten, YouTube'da çok güzel videolar var aslında.
Kontrol tekrar bu calculus on manifold olmuyor değil mi? O başka bir şey.
Yok, daha basit bir şey. Calculus on manifold çok daha ağır bir şey bence. Yani o differential geometriye girmeye başlıyorsunuz calculus on manifold'da. Kontrol integralde hala two dimensional plane'desiniz. Esasında elektromanyetikte yaptığınız şey, 3 boyutta yaptığınız şey 2 boyutta kompleks sayılarla yapılmış hali kastediliyor. Yani çok daha kolay bir şey. Ama bizde ders olmadığı için maalesef böyle eksik kalıyor. Böyle temelsiz bir şeyler anlatmak zorunda kalıyoruz. Evet. Güzel bir kitap vardır. Churchill diye bir adamın. Bütün dünyada kompleks analizde o adamın kitabı okudum. Çok merak ederseniz oraya bakabilirsiniz. Churchill ismi.
Meşhur.
Evet, meşhur.
Ama yani ben bir şey değil.
Asimptotik kararlılık tam olarak ne oldu?
Asimptotik kararlılık bilmiyorum ne oluyor. Nerede?
Diakonov'dan ve
Tamam asimptotik stability. İngilizce söylenmeyince çok böyle şey oluyorum. Bazen kafam karışıyor. Bir non-linear sistemlerde tek bir stability yoktur. Her equilibrium noktasının ayrı stabilitesi vardır. Tamam mı? Ve de her noktanın stabilitesini ayrı ayrı incelemeniz gerekir. Pendulumda mesela downward equilibrium stable'dır. Asymptotic stable'dır hatta. Ama upward unstable'dır. Pendulumda hiç friction olmasa ona hala stable derim ben. Çünkü diverge etmiyor. Lyapunov stability öyle tanımlanır. Diverge etmeme olarak tanımlanır. Şimdi pendulum aşağıda salınırken diverge etmediği için equilibrium point'ten stable olarak denir. Ama pendulumda friction varsa o zaman equilibrium noktasına gider her zaman pendulum. Equilibrium noktasında son bulur bütün trajektörleri. Ona da asimptotik kararlı denir.
Tamam hocam.
Tamam mı? Yani equilibrium noktasının etrafında dönüyor. Bir yerlere uçup gitmiyor. O zaman stable deriz. Tamam mı? Ama asymptotic stable ise equilibrium noktası etrafında uçuşsa bile mutlaka sonunda equilibrium'a gider. Tamam. Onu asymptotic stable diyoruz. Hazır mısınız? Hiç hazır gibi durmuyorsunuz. Zaten 46 dakika ama herkes gelmedi herhalde. Okay. So let us see our first example. Our first example is the following closed loop system. So we have a K. Now I have 1 over S plus 1, S plus 2, and S plus 3 here. And the task is here to investigate stability when k is between minus infinity and plus infinity. For all real case, we have to investigate stability using Nyquist criteria. Nyquist stability criterion. Okay. So when we have this type of example, the first thing that I have to do is to draw my Nyquist path. So the Nyquist path is a path which is going to cover the whole right-half plane. It's going to pass. Again, here you shouldn't consider that this is, so this curve is exactly on top of the imaginary axis. Okay, it passes through the imaginary axis and it covers the whole right-half plane and it has clockwise direction. Okay, this is my Nyquist path and it has infinite radius. Okay, and then what is our transformation? As a transformation, we are going to choose f of s, which is n of s over d of s. And in this case, it is 1 over s plus 1, s plus 2, s plus 3. Okay? If I expand this, then I will get the following. 1 over s cubed plus 6s squared plus 11s plus 6. So what I have to do here is to transform each part of this curve by this transformation, and then I can look at what that n is by looking at the number of encirclements of the point minus 1 over k. Okay? The first thing that I'm going to do is that I'm going to determine my p. P is the number of open loop poles encircled by gamma s. Okay? Or number of unstable open loop poles. So here, the open loop poles are the poles of that transfer function, and they're at minus 1, minus 2, and minus 3. Okay? How many times does this gamma s encircle these? So how many open loop poles does this gamma s encircle? 0. So in this case, we see that p is going to be equal to 0 for this example. That means that since we have n is equal to z minus p and p is equal to 0, we are going to get z is equal to n. Okay? So if I have one encirclement of the point minus 1 over k, then the closed loop system has one unstable closed loop poles. Okay? If I have 0 encirclement of the point minus 1 over k, then I can say that there are 0 unstable closed loop poles, meaning that the closed loop system is actually stable. Okay? So that means that z should be equal to 0 for stability. Alright? Or the number of encirclements of the point minus 1 over k should be 0 for closed loop stability. So now here, I would like to spoil the surprise first. Okay? And I'm going to draw the Nyquist plot for this system. Currently, you won't understand what I'm drawing here, okay, or why the shape looks like this. We are going to do this step by step in much more detail. But currently, I will just draw the curve that we are going to get. This point is going to be 1 over 6, and my curve is going to be looking like this. Okay, this strange thing here. As I told you, you won't understand how I can draw this thing. But this is going to be the result. After I transform this contour, by this transformation, I'm going to get this thing. And this point is going to be minus 1 over 60. So now let us try to make a stability analysis based on the Nyquist plot. Okay? The rest of the lecture, after doing this, I will try to explain how we can draw such a thing. Okay? But now I would like to show you how I can use this thing after I draw this. Okay? So now let me try to get the stability range for this system. I will take my minus 1 over k first in this interval. Let me say that minus 1 over k is between minus 1 over 60 and minus infinity. Okay? Let me say that minus 1 over k is in this interval. Okay? And then what I can do here is that I can get rid of -1 here, okay? And I can multiply all sides by minus signs. It is 1/60, and here infinity. If I multiply this inequality by -1, what happens to the inequality directions? They are flipped like this, okay? And then I can take the reciprocal of all elements here. I can write here k, I can write here 60, and I can write here 0. What happens to the inequality directions? They are again flipped, so we get, when k is between 0 and 60, how many times the point -1/k is it encircled by this curve? It is 0 times. So in this case, z is equal to n is equal to 0. So there are no closed loop poles. Z is representing the number of closed loop poles encircled by this transform contour. Encircled by the original contour. Okay? So here in this case, z is equal to 0. So the closed loop system is stable. So in this case, we have a closed loop stable system. And then I'm going to come to this interval. Okay? -1/k can be in this interval. And I have -1/k is between -1/60 and 0. If I do the same flippings here, inequality change directions, I can see that this is going to correspond to k between 60 and infinity. How many times is the point -1/k in this interval encircled in clockwise direction? It is encircled by 2 in clockwise direction. Okay, so I have z is equal to n is equal to 2, meaning that we have two unstable closed loop poles, meaning that the closed loop system is unstable. Okay, so we have an unstable closed loop system. Now I will draw the root locus for the same system. Okay? So the root locus is going to be drawn by using the open loop poles and zeros. Open loop poles are at -1, -2, and -3. And I will fill in the real parts here. I need to fill in these parts. So put arrows, and then the asymptotes is going to meet at the point -2, and they will have 60-degree angle. And these two are going to be like this. Okay? This is my root locus for the same system. Okay? Tell me what the k value here is. It is 60. Okay? So k value at this point is going to be 60, because when k is in this range, all of the closed loop poles are in the open left half plane, no unstable closed loop poles. But if k is larger than 60, I have two unstable closed loop poles. Okay? So that is how a Nyquist plot is going to be used. It's going to give us a similar thing to the root locus. It's going to be much less intuitive, but that is how we are going to use it. So now let us come to the original question. How can I draw such a thing? How can I transform that infinite semicircle by using this transformation into this thing? How can I obtain this? We are going to investigate it. So here, it is not really difficult. I'm going to be doing the same thing, but because at the end I'm going to do the same thing for everything, then I want to do it now.
Bir de şeyde bu f of s dediğimizde s term varsa bunu kullanamaz mıyız?
What do you mean?
Yani pol olarak veya zero olarak s plus 1 yerine s
Yes. So here, when we solve the Cauchy principle of argument, we have learned that the original contour cannot pass from a zero or pole of the transformation. Okay? So here, if this transformation has some pole at S, okay? If I have S plus 1, S plus 2, something like this is going to be one of our examples. we won't be able to use this Nyquist path anymore. Okay, there will be an open loop pole here. Okay, and in that case, my Nyquist path cannot pass on that pole. In that case, we would unfortunately have to modify the Nyquist path. And what we're going to do is that in an infinitesimal circle, I'm going to turn around that pole. Okay, so I have to either exclude it or include it, but I have to turn around it. I cannot pass on top of that. Okay.